Hey everybody, this is Mr. Oliver. This video is going to be the solutions to the AP Physics 1 Unit 4 review practice. So let's go ahead and get started. Okay, so this unit on linear momentum is one of our shorter units, and there's really not much to it, but the concepts are kind of wide ranging and they can apply the concepts in many different ways. And so for this first question, we've got two carts are heading at each other at the same speeds. The cart on the left is 2 times the mass of the cart on the right. When the carts collide, they hook together, so that means it's an inelastic collision. And if you remember inelastic collisions, if assuming that there's no external forces, that just means the momentum will be conserved, but the kinetic energy will not be conserved. Now, in this question, it simply says, assuming positive momentum is to the right, sketch a simple graph that represents the momentum of cart of mass m as a function of time before and after the collision. So first of all, cart letter m is this guy over here on the right, and it's moving at the velocity v. So momentum of that cart is just m times negative v. So the total momentum is a negative value that's equal to mv. Now, the question says, let's sketch a graph of the momentum. So, the momentum graph would start off at that negative mv number. So you would start off at some value down here, which is equal to negative mv, and it's going to be constant. And the reason why it's constant is because there's no forces to change that velocity. It's a friction-free environment, so it's a constant velocity, therefore constant momentum. Now, after the collision, they stick together, and this cart will add to the mass of this cart. And so whenever they stick together, you can imagine the two carts linking together and rolling as one thing. So you'd have 2m on this side and m on this side. So you'd have a bigger, heavier cart. And because this second cart on the left had the same velocity as the first one, this guy at the beginning has more momentum than this guy. And so because there's more momentum overall moving to the left, then that means that after the collision, the two carts have to be moving to the right. And so you say, well, how much velocity do we have? Well, if initially we've got 1 unit of velocity moving to the left and 1 unit of velocity moving to the right, but their masses are different, then that means that there's got to be some kind of a combination of a final velocity that's not going to be quite as much as either one of these independently. So the easiest way to calculate that is just to do a simple little inelastic collision calculation. Now I'll run through this first one, and later on we'll see other cases where we do the same thing, but I'm not going to spend the time to do that for all of them. And so if I've got 2m traveling to the right at a velocity of v, and I've got another m traveling to the left at a velocity of v, that's our initial situation. And then afterwards, the two carts are traveling together at some total velocity. I'll just call that v final. And so when we set up a conservation momentum problem, we just say P initial is equal to P final of the system. Well, initially over here you would have this momentum, which would be 2m times a positive v, plus a single m times a negative v is equal to 3m times v final. Well, if I've got a 2mv plus a negative mv, how much does that leave us? Well, that just leaves us with a positive 1 mv of momentum at the beginning. 2m minus 1m is 1m times v. And so that equals 3m v final. So I'll divide, I'm trying to find this final speed, that's what we're going to need to know. So I'll divide by 3m, divide by 3m. And so our final speed is, well, look here, the masses just kind of cancel, that's nice. And for our final speed of these two carts together, it's 1/3 of the initial speed of either individual cart. And so that's why I was kind of saying earlier that we only know that the final speed of these two things together has definitely got to be less than any individual velocity. And it turns out that it's 1/3 the velocity. It's kind of a proportion of the total mass is really what it is. And so that means that after the collision, cart number M, or cart letter M, which is going to be right here, it's moving to the right at 1/3 of the original speed. So when we graph that, we're going to have another horizontal line that's over here at 1/3 mv. Now you don't have to draw the vertical line, or only the horizontal line matters, but it just shows you that transition. Okay. Question number 2 is a similar kind of question. You've got two objects hitting this little glider. A glider is basically like a frictionless track that rides on air. It's almost like the air hockey things you see at the main event or whatever. But this is just like a lab kart track that floats on air back and forth. So there's absolutely no friction. This clay ball, clay means it's going to be inelastic and it's probably going to stick to the glider. The rubber ball is going to bounce. And so the question says, indicate the direction of motion of the glider after the collisions. And they hit the exact same time. And you need to explain why. Well, the easiest way to do this is to say that because that rubber ball changes direction, its momentum change is bigger. Because remember, a change in momentum is mv final minus mv initial. And so that if that rubber ball is initially traveling to the right, let's say at 10 meters per second, and then after it collides, it's going to be moving backwards, also at 10 meters per second. If I wanted to calculate the change in momentum of that rubber ball, it would be mv final. Let's let m be 2. Okay, so it'd be 2 times a positive, 2 times a negative 10. This is my initial velocity right here, and this is my final velocity. Okay, mv final, so it'd be 2 times negative 10, so it'd be negative 20 units, minus the initial unit, which would be 2 times 10, so that's a positive 20. So negative 20 minus 20 is negative 40 units of momentum, kilogram meters per second. Okay, so it has a big change in momentum. It's twice as much as its original. Whereas the clay ball, it's going to hit this thing and basically kind of stop. So you could kind of think of the clay as only having half as much change in momentum as the rubber ball. And because there's more change in momentum on the rubber ball than the clay, there's more of a interaction over here on this left-hand side than with the clay. And so overall, this system has to move to the right because there's more change in momentum on that left-hand side than there is on the right-hand side. And so that's kind of a real subtle thing. And if we did a calculation, go through all the numbers, we'd see it, but they don't give us enough information to really tell. So what you need to say is the rubber ball always has a larger change in momentum. Specifically, if you think about it, change in momentum is the same thing as the impulse. It's almost like the bigger this number, the harder it hits. Because remember, the impulse is F times time, or F average times time. A rubber ball hits harder than a clay ball does. Just like, if I collide and stick with, if I play baseball and I use a rubber baseball bat as opposed to a real baseball bat, the real baseball bat is going to make the baseball go a lot farther than the rubber one will. Right? So the more bouncy the collision, the more impulse you have. Right. The next question, number 3, we've got a force versus time graph. And what they ask us to do is to determine the net change in speed of the spacecraft. Net change in speed. Okay, so first of all, let's understand what the graph tells us. The graph indicates a force and a time. This is an impulse graph. Anytime you have force and time being graphed, that's an impulse. And if you remember, impulse, which is equal to the area under a force versus time graph, will also be the same thing as the change in momentum. Okay? And going one step further, the change in momentum is going to be mv final minus v initial. That's what a change in momentum is. So, in order to find the net change in speed, which is this term, that's delta v, I need to know the change in momentum. And to get the change in momentum, I need to know what the impulse is. And to get the impulse, I need to know the area. So ultimately what you conclude is that m times delta v is equal to the area under this particular graph. All right, so now it's just a matter of saying, well, what's the area? Well, if you look at it, it's kind of a ill-defined graph, but you can kind of see that it kind of goes from 100 to 2 for a little bit of time, so that's kind of a rough approximation. And then it's kind of flat for a second, nothing really happens there, and then it kind of jumps down immediately, and then it's kind of like a boxy shape for another second. So if I can find the area of this triangle and this box, that would be the total area of this the spacecraft going from 0 to 4 seconds. Okay, so let's just label these two areas real quick. I'm going to label this as area 1, and I'm going to label this little box as area 2. And so area 1 is 1/2 the base times the height. And that's going to be 1/2 times 2, it's 2 units in the base, times the height of 1,000. So half of 2 is 1 times 1,000, which is 1,000 units. So that's the area of the first one. The second little area is this little box right here, and it's got a base times a height, or length times width. It's got a base of 1 unit. That's the time between 3 and 4. And then the height is -500. And so that gives us -500 for the second area. And so the total area, that's kind of what this is right here, the total area total, is the sum of these two. So the area total is equal to 500. And the units are Newton seconds of area. And so now I just need to divide that number by the mass to get the change in velocity. Delta V is our area divided by the mass. So we got -500 divided by the mass of 4,000. And that gives you 0.125 meters per second, because it is a speed. All right, and that is an estimate of the net change in speed. Specifically, it's a negative, so you lost that much velocity. Okay, question number 4. 2 identical carts are free to move a straight frictionless track. At time t1, cart is moving at 2 meters per second. When it collides and sticks to cart y, which is initially at rest, sketch a single velocity time graph that shows the velocity of cart x before and after the collision. So we're looking at a velocity time graph, all right? And we're thinking about cart letter X. So here's the idea. Here's cart X, here's cart Y. Cart X is going to come along and hit, and then they're going to move together in an inelastic collision. So if you think about it, cart X has to be moving fast at 2 meters per second for a while, and then after it collides with another cart that's the same amount and it's sitting at rest, that means that afterwards those two carts have to share the same momentum that it started off with. So if you've got 2 meters per second with a certain mass, let's say the mass is 1 kilogram, and then all of a sudden you're sticking to something, so you're now twice as heavy because it sticks to a similar cart, then that velocity has to decrease exactly to half of the original velocity, because now you're splitting up that original momentum into 2 carts as opposed to a single one. So your scaling here for that second segment should be half as much as the first. All right, question number 5 has a little spaceship. And the question says there's this spaceship with a little shuttle pod. They're both moving to the right. The mass of the pod is a small mass, little m. The spaceship is 6m. The pod is launched, and afterward the pod is moving to the right with speed vp, and the spaceship is moving to the right with speed vf, where vf is greater than v. So basically what happens is these two things are going along together, and then it drops off the little mass at the bottom, and it's still going to move forward but slower, but the top half kind of starts, it gets to go faster because it has less mass to it. So the question says, after the pod is launched, is the speed of the center of mass of the system greater than, less than, or equal to? Well, this is a key point of conservation of momentum. We say that momentum is conserved. In other words, P initial equals P final if the force external, in other words, air resistance, friction, gravity, all that stuff, equals 0. We assume that it's negligible. And if you remember when we did the lab, we had to make sure that the track was not tilted when we did our conservation of momentum lab, because if we had a tilted track, then you'd introduce gravity, which would be an external force, and momentum wouldn't be conserved. But here's the point, is that if there's no external forces on the system, can it speed up? Can it slow down? Well, no, because there's no force. There's nothing to change its velocity. And that includes the entire velocity of the whole system, specifically the center of mass velocity. So, what you conclude, because there's no external forces, the center of mass velocity is unchanged. That's a big key idea of conservation of momentum. Because there's no external forces, there's nothing to change this quote-unquote center of mass velocity, or the total velocity of the system. It doesn't change at all. All right, question number 6, kind of a similar question. We've got this train car, and inside the train car, we've got these 2 objects that are rolling towards each other. And then it says, what is the velocity of the center of mass of the spheres in this frame of reference of the train? So looking at it, like let's say I'm riding in that train car and I saw these two little balls rolling toward each other. Well, if I've got a certain velocity going to the right and a certain velocity going to the left of 2 identical spheres, then my center of mass velocity would be right in the middle, and it would be 0. So from the train's perspective, train frame of reference, V center of mass is 0. It's not changing. It would be just like if I saw 2 objects coming together and hitting and nothing happened. But then, if I'm standing out here watching this, as that train's going by at this speed v, vt, it's kind of hard to read there, then I would see this whole system as moving with some velocity. And so from the person's frame of reference, the velocity of the center of mass would be the same velocity that the whole train is moving at. So a difference of perspective does matter when you're thinking about a center of mass velocity. In the train's frame, there are no external forces, and so the center of mass velocity is constant. For the person's frame, there is a force being exerted. There's probably some force of the train making this thing move, and so that means that that center of mass velocity could be something different. Okay, so on question number 7, we've got a cart hitting a force sensor, and this is just a matter of, do you remember what a typical graph that represents a collision looks like? And so that's where we go back to talking about impulse graphs that have force versus time. And if you remember, for any kind of typical collision, that kind of collision is this kind of spiky looking graph. And the harder that collision is, the more rigid that kind of collision is, the spikier this graph. Now, if I put a piece of clay on the front of that cart. I think I did this in class. We put some clay on the front of it. Whenever it runs into the force sensor, it kind of changes the way this graph looks. In fact, what happens is with the clay, you don't get this really sharp spike. You get this kind of elongated, it kind of spreads it out a little bit and makes that overall maximum force less. And it's just like when you have an airbag in your car or you're landing on a net or something like that. It reduces the overall force. All right, question number 8. We've got a rate of change of linear momentum of the sphere versus time. It says the graph above shows the rate of change of linear momentum of a sphere of mass m as a function of time after being dropped from rest near the surface of the Earth. Okay, so that's really key thing. It's dropped from rest near the surface of the Earth. So if it's dropped from rest, what force is acting on it? Well, that's the pull of gravity. There is a constant pull of gravity pulling this thing down. And so that's why this line would be constant. The change of linear momentum, this is actually another key point. The rate of change is just how much the momentum changes in time. Well, if you look at it, look real close at what it says. The unit is a Newton. So it kind of even gives you a hint that this term, this rate of change of linear momentum, is a force. It tells you that this is a force versus time graph. They just put it in different words. It's a Newton versus seconds. And so, because it's a force graph, we can find the velocity of the sphere by recognizing that this area right here, which is our impulse, the impulse is always equal to the change momentum. Okay, so what's our impulse? Well, that's 15 units, 15 Newton seconds. And the change momentum is going to be mv final minus mv initial. Well, the initial velocity is 0 because it's dropped from rest. And so if I want to find the final velocity after 3 seconds, I just take my 15 divided by the mass. Well, how the heck do I get the mass? Well, I know what the force of gravity is. It's 5 newtons. Because that's what this term is, the rate of change of the linear momentum of the sphere of mass m. It is being pulled by gravity because it's being dropped from rest. So I know what the force of gravity is. It's 5 newtons, and that's just mg. So therefore the mass is just 5 newtons divided by g. And guys, let me kind of give you a little hint. Let's just use 10 for g. It's okay if you use 9.81, but if you use 10, they will accept an answer. So I'm gonna just round up and see it even says it here. Assume g is equal to 10. So that means our mass here is 5 over 10 kilograms. And so that means that it's 1/2 a kilogram, or 0.5. So when I plug that into here, 15 divided by 0.5, our final velocity will be 30 meters per second. All right, so the actual mathematics is not hard. It's just trying to understand really what it's asking. Is that they give you some weird words, but you just need to see. It's like, oh, that's a Newton, so that's a force. What kind of force is it? Well, it's being dropped from rest near the surface of the Earth. Oh, that's the force of gravity. That's 5 newtons. And so they give you everything you need. You got to interpret it. Question number 9. We've got a perfectly elastic collision with mass m traveling at a speed of v naught in the x direction, and it strikes an object with a mass of 3m that's initially at rest, and then we need to figure out what happens afterwards. What happens to mass m? What happens to mass 3m? All right, this is actually a pretty tricky question, so I'm going to give you a couple of special equations for this. Whenever you have this situation, for one, it has to be stated that it's an elastic collision. and it states it is perfectly elastic. So that means kinetic energy is conserved and momentum is conserved. So you would say P initial is equal to P final and K initial is equal to K final. And so you would write some big set of equations that describe all this motion, but the problem is they don't tell us anything on the final side. So it ends up where you have to have a system of equations that you solve, and it turns out to be pretty nasty. Now, another thing that you need to do is recognize that the second object is at rest. And if we have that scenario, if we have this particular thing where one object's sitting still and the other one comes in and hits it, then I'll give you a couple of little super special secret equations. And what this is those two systems of equations that are solved. So if I call this first object number 1 and my second object number 2, I can find the final velocities of these two objects with these super secret equations. V1 final is going to be the mass of object number 1 minus the mass of object number 2 divided by the sum of the masses. So it's the difference between 1 and 2 divided by the sum times the initial velocity of that first object, VO. That's this guy right here, VO. Right? And so that'll tell you how fast that first object's moving after the collision. And then for the second equation, you'll have 2 times the first mass divided by the sum, m1 plus m2, once again multiplied by the initial velocity. And so these two super secret special equations are a result of this information that they give us. All right. So I would say that, I just have this on hand for checking what happens. But in this case, it actually asks us to calculate something. So when you plug these numbers in, you end up getting that the first object will bounce backwards because it's lighter than the second one, and it's going to go backwards at half its original speed. So it's going to be minus 1/2. And the second object will share that initial velocity the other way. So it's going to be 1/2 v naught the other way. And so that's kind of one of these weird scenarios where if you don't know the equations, you just kind of got to look at the proportion of the total amount of velocity. And it's proportional to how much mass you have. This object is the second object is 3 times as big as the first. The velocities end up being half and half. All right. Number 10, we've got an ice skater moving the velocity v across an icy pond. The skater throws a snowball directly ahead. Determine the velocity of the center mass of the skater snowball system immediately after. Assume friction and air resistance is negligible. So when it says assume friction and air resistance are negligible, you can automatically make the statement that the net external force is 0. And in that case, the momentum is conserved. P is conserved. And if that's true, then you can say that V, center of mass, is constant. There's no forces to slow the system down, so it stays at its same speed. So the final velocity is just what it was at the beginning. V. Doesn't change. Okay, number 11, you've got block A and B going through a collision. And it asks, what is the magnitude of the net force exerted on block B, and why does it have that value? So here's the idea. When you have two blocks that hit each other, regardless of how much mass they have, let's say that this one is little m and the second block is 2m. When this thing hits the second block, there's an interaction, there's a force. And according to Newton's third law, regardless of what kind of collision you have, regardless of how much mass you have, you need to conclude that there's always an equal and opposite reaction. right? So if it says that block M collides into block 2M with a force of F, I guess this is A and B rather, block A exerts a force of F onto block B, then you can conclude that block B, through this equal and opposite reaction idea, exerts the exact same force onto the other one. There is no two interactions. There's only one interaction. That's why I use the word interaction. So whenever you have two things that come together and smash into each other, when you have that kind of collision, there's only one force. One points one way, the other points the other way at the same amount. All right, and don't forget that. That's really important in any time of any kind of collision or two-body interactions. All right, question number 12. We've got some data. There's two carts. Each cart has a mass, 5 kilograms and 1 kilogram. They both have the same force. They give us the change in momentum and average acceleration of cart 1, and then it asks to find those two values for cart number 2. So what we need to do is, in this case, they give us all this information for cart number 1. And so I'm going to use impulse momentum theorem, which says the average force times the time interval is equal to the change in momentum. Okay. The only thing we don't have on here is change in time, so I'm going to solve for the change in time, and this is going to be for cart number 1. So our average force is 15 newtons. Our change in momentum is 0.3. So 15 over 0.3 gives us a change. Oh shoot, I did that backwards. Delta P over the force, sorry. So it's 0.3 divided by 15. And that gives us a time interval of 0.02 seconds. All right. Now it does say that the force is the same for the second cart. And it's a collision where the tracks head on. So that shows you, yeah, once again, there's an equal and opposite reaction. So what I want to know is, what is my new change in momentum of cart number 2? Well, cart number 2 collides with cart number 1 with the same amount of time. So delta P is still going to be my average force, and it's still going to take the same amount of time. So we're going to have 15 times the same amount of time. Hey, look at there. The change in momentum is exactly the same, 0.3 kilogram meters per second. And it shouldn't be any surprise that just because there's two different carts, if they're undergoing the same forces and the same time interval, they're going to have the same change in momentum. Now the velocities and accelerations and stuff like that will be different, but delta P stays the same. And so lastly, to find the acceleration, that's just F over M. So that's just 15 divided by 1, which is 15 meters per second squared. So that's for cart number 2. Just to check, what was the acceleration for cart number 1? Well, that's F over mass number 1, so 15 divided by 5. And so for the heavier cart, it had a much less intense acceleration. And so that's how you see the differences. Yeah, the accelerations are going to be different, but the forces are the same, and the changes of momentum are the same. This one right here was 0.03, or 0.3. Same value both times. So remember that. Any kind of interaction, collision, there's always the same change in momentum for both objects. It's just the end result, the accelerations or velocities are going to be different. All right, question number 13. A 1 kilogram lump of clay is sliding to the right on a frictionless surface with speed 2 meters per second, collides head on and sticks to a 0.5 kilogram metal sphere that is sliding to the left at 4 meters per second. What is the kinetic energy of the combined objects after the collision? So if I need to find kinetic energy, I need to know the masses, so I know the masses, and I need to know the velocities after the collision. So I need to find final velocity. So we're going to do that using momentum. P initial equals P final My initial momentum is 1 kilogram times 2 meters per second, because that's its initial speed. It collides and sticks heads on to a 0.5 kilogram metal sphere traveling to the left. So that's a negative 4 meters per second. And that's going to equal, because they stick together, it's going to be equal to their combined mass, because it's inelastic, times V final. All right, and so when we work through this mass right here was 1, and this was 0.5. You end up calculating that this entire left-hand side of the equation, what is that, 2 plus a negative 2? Well, that's kind of interesting. That's 0. So that means initially there was no momentum. And if there's no momentum at the end, then no matter how much I do on the right-hand side, because that sets it equal to 0, we must conclude that the final velocity must be also 0. And if that's true, then the kinetic energy after the collision is also 0 joules. Question number 14. 2 identical blocks with mass 5 kilogram each are connected to the opposite ends of a compressed spring. So this is kind of what it looks like. I'm kind of surprised they don't give you a picture, but you got this mass with a compressed spring and another mass. And then the blocks initially slide together on a frictionless surface of 2 meters per second. So they're sliding to the right at 2 meters per second. The spring is then released by remote control. At some time later, the left block is moving 1 meters per second to the left. The other block is moving to the right. What is the speed of the center mass of the system at that instance? Okay, once again, the center mass velocity problem. What you need to ask is momentum conserved? Well, are there any external forces? Well, it's a frictionless surface. There's a spring here in the middle, and it's going to produce an internal force, but external forces are 0. So that means that momentum is conserved. And if momentum is conserved, then the center of mass velocity is constant. So it must be the same as what it started with, 2 meters per second, regardless of what happens after the spring is released. Who cares? Okay, next question. We've got a graph of position versus time. And it's the horizontal position is a function of time for the center of mass of a system of particles of total mass 6 kilogram for a very short time interval around 2 seconds. So that's right here during that time interval. An external force is exerted on the system. So it's an external force. So that means it's going to change the momentum of the system. Okay. So how do I get that? How do I get a change of momentum? Well, I'm looking for delta P, which is equal to mass times the final velocity minus the initial velocity. Okay. So how do I know what the mass is? I got that. So how do I get final velocity? Well, I get that from this graph. Pardon me. I can get velocity from the slopes. Remember, the slope of a position time graph gives me the speed or the velocities. And so all I need to do is calculate the initial and final slopes. And so the final slope is going to be this green line right here. And so that's got a rise over a run of, so that's an 8, so that's 9. So it's a rise of about 3. That's in the middle. And the run is 1 second, 2 seconds, 3 seconds. So the rise over the run, or the slope of this guy, is actually -1. Okay. And the rise over the run of the first part is, well, that's a 2 units high divided by, or no, not 2 units, so it's a 4 units high divided by a run of 2. So that's a slope of a +2. +2 here. This was -1. So -2. So -1 minus 2 is minus 3 times our mass, which is 6 kilograms. And so that means our change of momentum is equal to minus 18 kilogram meters per second. Okay, question number 16. Got just a little bit more here, guys. We've got another force versus time graph. Sketch a graph that represents the wagon's momentum as a function of time. Okay, so here's kind of a little bit of trickery when you have a force versus time graph. Think about it like this. A force is equal to ma, right? Newton's second law that this is force equals ma. So I've got an a essentially on this axis. Yeah, it's multiplied by the mass, but this is like an acceleration versus time graph. And we want to find a momentum graph. Well, momentum is mv. So if I could take these numbers over here and divide by mass, I would get an acceleration graph, right? So I could kind of pretend, ignoring the numbers a little bit, I could pretend that my acceleration graph kind of looks like this. It kind of goes up, that's kind of linear for a second, and then it's kind of flat. So my acceleration graph would be flat for a little bit, for a couple more seconds, and then for the last 2 seconds, it kind of goes up again. It's kind of steep like that. So that's what would happen. If I took these numbers and divided by the mass, I'd get an acceleration graph. Well, if I want to get a momentum graph, I could kind of do the same thing by dividing by the mass. And so I could get what the velocity graph would look like if I took the momentum numbers and divided by the mass. And so if I had a velocity versus time, then I could say, hey, that's kind of how we did it in kinematics. Because remember, like if I had a constant acceleration during that time, that would correspond to this little segment of time right here in the middle. And if I have a constant acceleration, that means I have to have a linear velocity. And if I have an increasing acceleration, then that means that this would have to be some kind of a parabolic curving upward graph. And then over here, this would also have to be kind of curving upwards. Okay, and so this is just kind of a graphical analysis kind of thing, regardless of what numbers are, because it just says sketch the graph. That if you know how a changing speed occurs when you have a certain acceleration, that's kind of the idea, is that you're always going from like more complex, more exponential terms down to less ones. Because like remember, if you look at, let's just do it on this thing. If you have a position versus time graph, a velocity versus time graph, an acceleration versus time graph, if the position graph is parabolic, the velocity graph is linear, and then the acceleration graph is constant. Okay? And so when you saw that acceleration graph over here be constant, the velocity graph was linear. And then when you saw the acceleration graph be linear, the one that's above it, the velocity graph, is parabolic. Okay, and that's kind of the way that's what this question is asking about. It's can you interpret a graph without using numbers? Can you just look at it and say, hey, that's a linear function, so the one above it, the one of lower orders of magnitude, that would be a parabolic. All right. Question 17. Once again, we got another impulse graph, but this one's a little tricky. You got to watch out here. Notice the units on that particular graph are in milliseconds. So if I want to find the speed of the ball after the collision with a rocket or with a racket, I'm still doing impulse. J is equal to the area, which is equal to the change momentum. So the area of this graph is 1/2 times the base, which is 8 milliseconds, so that's 0.008, times the height, which is 500. And so that's 2 Newton seconds. That's our impulse. And so I just need to set 2 equal to mv final minus mv initial. And so I know all these values except for the speed after the collision. So I don't know VF. So I'll do 2 is equal to the mass, which is 0.05, times VF, minus the mass, which is 0.05, times the initial velocity, which was 10, but it's moving to the left at 10, so that's a negative 10. All right. And so after you go through and do your calculations, you'll end up finding that V final is equal to a positive 30 meters per second. All right. And our last question of the day, we've got a mass of 2 kilograms traveling to the right. So we'll close out with typical head-on collision. So this is object A. It's traveling to the right, and it's got a mass of A. We'll call mass of A is equal to 2 kilograms. It's traveling to the right, so its initial speed of A is 3 meters per second. And it collides with object B traveling to the left. So here's object B traveling to the left. Its initial velocity is also 3. Traveling to the left at 3 meters per second. So I'll call it V initial of B. And mass of B is not known. Okay. It actually asks you to determine 2 answers that could be the mass of object B. Well, let's do the obvious one first. Let's assume that this collision is elastic. Okay. What is it if it's elastic? Okay. So what I'm going to do is I'm going to say P initial is equal to P final. And so this would be 2 times 3 plus negative 3 times mass of B would equal 2 times negative 3 plus 2 times positive 3. So what I'm doing here is I'm assuming if these are elastic, that their velocities are going to swap. And if they're elastic and their velocities swap, that would be true if this mass was 2 kilograms. Okay. Okay, so the only way for this to be true is if this is 2 kilograms, because it does say afterward each speed has a 3 meters per second, a speed of 3 meters per second. I just said that, oh well, their velocities have to flip around, and the only way for that to be true is if this mass is also 2 kilograms. So the idea is you got these 2 balls, they come in here and hit, and then bounce right off. It's like 2 cue balls on a pool table going beep and bouncing off. Okay. Now the other solution's kind of dumb, but you could also say that it's an elastic collision or an inelastic, and the only way that they would both have the same mass is if mass B was like super tiny, like 0.0000000000001 kilogram. It contributes basically nothing to the collision. So there's B, that little tiny speck there, and here's A. And so in that case, if they were inelastic and they stuck together, they would both basically have 3 meters per second to the right. If the mass of the second object is insignificant to the first, then when they stick together, they'll both have the same velocity. Okay, and so that concludes the solutions for this unit. I added a few extra questions in there, but I felt like during the school year we kind of just blew past this, so I wanted to let you see some extra stuff. So if you have any questions, just please let me know, and I'll see you next time. Bye bye.